your questions, people. I can
Hello?
see that we have special. Yeah, please, come on.
Yeah, this is Graham here.
Yeah, Graham.
I really, yes.
Hi, Graham.
I'm in Europe,
Hi,
so
I didn't see you there.
for me.
Hi, Graham.
Yeah, no problem. Very nice talk, William. Actually, it was
Thanks,
sort of
Graham.
interesting when you had mentioned Platonic solids or Platonics, because Ross has referred to that as photonics with the plate equation. So to begin with, I had a completely different idea. But anyway, it was very nice. So I had two questions, one on the first part and one on the second part. On the first part, one of the things we found, which is also why we called it active exterior cloaking, is that there were sort of throats that connected the cloaked region with the outside region that were sort of dependent upon the level of truncation.
Yeah.
And I presume you find these throats too. We didn't have a quantitative assessment to whether they were, how wide they were. But do you notice sort of numerically whether those sort of width of those throats, what they are for the different sort of Platonic solids you have? Anyway, that's one question. And then the second part, I thought it may be sort of interesting. You have two spheres with a narrow gap between them. But if I have like cavities in my elastic solids, which are sort of air, it may also be interesting having a narrow, I'll call it a throat between them two, so that air can sort of pass from one to another and be a little bit like a standard Helmholtz resonator, you know?
Yeah. So
anyway,
great.
That's my questions.
Thanks.
The other thing, I liked your covoid, because it sounded like COVID.
That's right. That was somebody did mention that. I wonder whether anybody had seen it, but we wanted to avoid it. Yeah. But okay, so as regards we do get those throats, yeah, and we always get that issue of, practically how big is the field going to be within the actual active source zone. Now, we haven't actually looked at the dependence of the truncation, of that throat width on the truncation, but we should do that. What Chutkim did do a lot on was the dependence of the truncation of the field, on the kind of active source coefficients required, so to speak, in order to get a certain kind of error. So that's all going to be in the paper. But we didn't look at the dependence on the throat zone. So yeah, that would be a great thing to look at. I agree. As regards the resonance, yeah, I agree. I mean, I think you could do all sorts of things. One thing that we really want to do is to look at if you combine because this is obviously classical monopole resonance. If you combine that with the standard, rigid and soft resonator, which is the dipole. So then you're kind of able to then exploit both the monopole and the dipole resonance in elasticity context, which would be quite neat if you could have a metacluster that was combined of the two.
Yeah, I guess my question was more to where looking at the sort of case of intersecting holes, but it's much more difficult mathematically to sort of treat that.
Oh, so you mean actually, so if you have your two voids and you literally have a gap between them.
Right. So air can sort of rush between one side to the other.
Yeah.
Like blowing over a jar, right? It's a little bit like a Helmholtz resonator.
Yeah, I think that would be interesting. I think so we thought quite a bit about the dumbbell kind of resonator as well, because what you really want, so two voids, throat between them, so you can actually perhaps exploit some kind of thermoviscous loss, in the actual connectivity zone.
Yeah. So the dumbbell, did you find anything qualitatively interesting? That does sound so more or less what I was thinking of about.
Yeah, I think that we haven't done that, because the thing is, we've done lots of work associated with thermoviscous loss in a tube, You know, so I think what you could do is do some nice matched asymptotic where you had, you know, two voids throughout, you know, connect the two via the kind of source coefficients at either end of the voids. I think that would be a really nice problem, actually.
Yeah. Oh, well, anyway, thanks for the talk.
Thanks, Graham. Much appreciated.
Yeah.
Any more questions? I'm sure there are many, many questions. So once again, this can be naive questions or more advanced ones like Graham's questions. Any question would do. It's a great opportunity. Come on, people. Okay, so I've got a naive question. So this is for acoustic waves, but of course, this kind of geometry would be very well suited to electromagnetic waves as well.
Yeah.
Well, now you know you have to turn this into curl. So do you know any kind of work on these electromagnetic active sources?
That's a good question, Seb. I think so. I think there's been quite a bit, but I can't. Graham would probably know better than me, actually. I mean, pretty much most, like you say, most of the work is pretty much, you know, you can translate it across, can't you? All you have to do is fiddle around with your vector potentials, I think. I mean, there's not much work that you'd have to do, I don't think. Certainly in 2 dimensions, loads has been done. I'm not sure about 3D.
But I'm speaking of 3D because in 3D, really the vector nature of the Maxwell system, you know, now you really have, you can't play the usual trick of, you know, correspondence between acoustics and electromagnetics. This would break down.
Precisely. Yeah, exactly. Yeah. But I agree. I think, you know, I think there's lots to be done. I mean, the key thing in 3D is literally the complexity of the mathematics. I mean, there is an argument to say, you know, because there's been lots of work done, you know, ISVR, for example, in Southampton, associated with kind of standard active cloaking, and of course, there's the alternative approach to active cloaking from Sasha Movchan's group, where you know you literally just take the kind of monopole dipole, for example, and you try to optimize that given an incident field, which is a kind of, you know, sensible thing to do from a practical perspective. That's kind of an alternative way to do things. And I think, you know, from a computational perspective, then there's some merit in thinking, you know, that's an alternative approach. I mean, I think this is kind of mathematically elegant way of doing things. And you know, the nice thing about it is it is exact, essentially.
And I've got another question. What happens now if your background medium is not uniform? You know, let us imagine that the background medium is heterogeneous.
In the active source case, in the active cloaking case.
Yeah.
Good question. I guess. Okay, so I suppose it depends if you can define it in terms of a effective medium, or do you mean like some kind of stratified
I guess that to apply all this machinery, you would need to homogenize it first, no? I mean, you need some kind of constant parameter, even if this parameter is anisotropic, matrix valued, it cannot be spatially varying, no?
I mean, the important thing is that you know what the incident field is. So as long as you know what the incident field is at the active source location, then you're fine. So essentially, if you can solve your wave propagation problem in the exterior region, then it doesn't matter what the exterior region is, I suspect.
Even in the close proximity of because in the close proximity of the source, it should be constant, or it can be, you know, slightly heterogeneous.
I don't think it matters, Seb, really. I mean, as long as you know what that field is, well, okay. So in principle, you can solve the problem for any incident field. So it doesn't have to be planar. So the trick, I guess, is to actually know what that incident field is. So if you think practically, what you'd do is put two sources or several sources further out, you know, so that they could do some form of measurement of the incoming field, right? So the problem would be is if that is representative of what the actual active sources would see by the time the field gets to them, if that makes any sense.
Yeah, it seems okay. And
you know, so if the field came in and that region of sensors, you know, would then presumably send signals to the active sources to do certain things, because, you know, you're anticipating a certain incident field. But by the time the incident field gets to the scatterers, you know, it may have been transformed because it's no longer a homogeneous medium. So that's an interesting point, actually. Yeah.
Okay.
Yeah. That is an interesting point. Yeah. It seems that you know what the incident field is exactly.
Yeah, because we've been thinking of these problems in well, in terms of the diffusion medium, you know, that's we've been thinking along these lines. And
for active thermal sources, you mean?
Yeah, but in a diffusive medium.
Okay. Yeah.
And anyway, it's interesting.
A medium that's heterogeneous.
Yeah. So diffusive, so random, heterogeneous, random.
Oh, diffuse. Okay, sorry, I thought you meant diffusive as in, you know, as in the heat equation.
No. In fact, just think of a random medium, and you've got your active sources in a random medium, or heterogeneous, but highly heterogeneous. So
is it sort of statistically uniform? You know,
yeah,
so
you might wish to have these kinds of assumption, you know, effectively but yeah, we were thinking first in terms of this one-step homogenization approach, and then, you know, starting from there. But it's not totally obvious, you know, how to push forward.
It depends what frequency content your signal's got.
Again, well, of course.
If you're
if you're high frequency, you have it.
yeah, exactly. Yeah.
But let us imagine that you have you know, a wavelength which is large compared to the typical heterogeneity size. So somehow you can, you know, apply some, you know, averaging techniques, even if the medium is random. So, and then possibly you can define some cloaked region with active sources. Yeah.
So you're interested in the transition between when it's a good approximation to homogenize in the exterior field.
Definitely. Yeah. Anyway, so please, people, ask your questions, because you know, we have a specialist of cloaking and many other topics in well, multiple scattering. So you should use this unique opportunity, this great opportunity to talk to Will.
I've got a question, actually. So I asked Graham this question a couple of days ago. So it's about work on neutral inclusions, experimental work on neutral inclusions.
Oh, wow.
Okay. So whilst people are here, so Muammer, looking
Muammer,
Nance's here.
Come back, Muammer, please.
So this is the bit where I get to see if anybody's still there, because I've asked the question.
Yeah, and Muammer is still there.
Sorry, I'm here.
No, it's fine. So Muammer, do you know of work on experimental work on neutral inclusion? So I know a little bit, and obviously Graham pointed out Martin's lovely work on kind of pentamode.
Well, we did the pentamode case. So for in the limit of the elasticity for the pressure waves, you can have this neutral inclusion, but for the pentamodes. Otherwise, you can have it for out of plane shear waves. So this is then strictly equal to the so we did this stuff. We did it for the diffusion, photon diffusion in optics. So you have also some work on thermodynamics, on heat diffusion, for which it works too. And then I think there there is some work by Mopshan on the case for pressure waves where you actually need some anisotropic coating for this to get this to stabilize it.
But he did it, Will, actually.
Sorry?
Will worked on this. You worked on this kind of stuff, Will, yourself. With,
so you can get these. You can get these kind of interface. You can have a sort of artificial interfaces. I'm amazed that nobody's kind of, or not that many people anyway, have sort of looked at it from a kind of composites perspective. Kind of, because that work that you did, Mama, was really lovely with pentamodes. But from the viewpoint of having a particle or a cylinder or just something else and another medium that's coating it, there's very little. There's a bit on plates, so that dates back to kind of 1950s. I think this is where the work originated in plates, but I can't find anything
on the composite. There is a nice chapter in the book of Milton in the 2002 theory of composites.
That's kind of the.
But it's true that there has not been any real experiment of having multiple inclusions.
Yeah, I'm just surprised. It might have happened, but I might have used the wrong terminology. People may used a different phrase for the coating. That's the thing. I need to work out what people in the composites community call it. They probably don't call it neutral inclusion. They probably call it something else, stress reducer or something like that.
That's correct. Yes, and basically in electromagnetism, they call it rather scattering cancellation or stuff like this. Which at the end turn out to be the same. I mean,
So that's the interesting thing in elasticity. They're not quite the same because this kind of near field effect that you get. But anyway, it's okay. Good. Well, I'm glad that it's not obvious. Anyway, that's a result in itself.
There's also there's also the work of Ingeta and Alou, where they look at basically the coded spheres for electromagnetic scattering and show that the cross section is 0. But I'm not sure whether maybe one of you would know whether that has been experimentally verified. I think it has, but I'm not sure of the reference.
And by the way, Graham, do you know some work on electromagnetic cloaking, active cloaking in 3D?
Well, yes. I know. Well, it's not really 3D. I'm sure I would mispronounce his name, but this electrical engineer, George Eleftherides, Greek guy, I'm sure you know his name, and I'm sure I'm mispronouncing it, but he did a Miller type and a experimental result of Miller's type of cloaking for electromagnetism. I don't have the precise reference that on the top of my head, and but I'm sure if you contacted him, you could find the reference. So yeah.
Oh wow. Okay.
It might be worth.
It's not.
Has Daniel Onofray done stuff, Graham? I'm sure he's submitted some stuff to Wave Motion actually. It wasn't active cloaking. It was more about control rather than active cloaking. But I mean, it's the same kind of thing. You're trying to either beamform or do something in terms of waveforming.
Right. Yeah, he attained some very interesting results that for this active sources
just
that
with
would
one
suffice
source,
to have. Sorry?
He made it just with one source. No, you can cloak with just one source. It looks to me, no?
Exactly. That's what I was about to say.
Yeah.
It's crazy,
sort of
this article. It's crazy. I mean, it is totally unstable, no?
Well, I think you have to go to extreme, it must be very unstable and have to go to extremely high order. And maybe I have to
infinite order.
Yeah, I think it's I mean, normally when one truncates a Helmholtz expansion, it's sort of a sharp truncation. but of course you can consider things which are sort of more smooth truncations and things, you know, and yeah, so
yeah. I think that's the other interesting thing about the active cloaking is that there's a natural tendency to want to, as you say, going to truncate at n, but actually, you know, it turns out you could choose 0, 5, 18, you know, in it. That's the kind of more optimal way. I think that's what some of those plots that I had showed, that it's not always optimal to choose 0, 1, 2, 3, 4. You know, you could choose 0 and 6, and that would actually get the dominant contributions. It depends on your incident field and your, you know, distribution of sources.
But,
interesting.
Okay, Graham, apart from this very extreme case, in your opinion, and okay, in the opinion of Will, how many sources do you need to cloak an object in 2D and in 3D, realistically, in something which is meaningful physically, I mean, experimentally? How many sources would you need in your minimum?
Well, it sort of depends on the size of the object. I mean, what Will is trying to do is sort of maximize the so-called quiet zone. And the higher the Platonic solid, the better you're able to do that. And that's what Will has shown.
Yeah.
But at the same time, and I guess Will's just about to take over here, but at the...
Well, I was just going to show that plot, really. That was the kind of... That was the one I was thinking, purely because, you know, I mean, I'm not an experimentalist by any stretch of the imagination, but I think practically, you know, in acoustics, for example, monopole and dipole is kind of achievable. Certainly these days, you know, it's easier. But that kind of illustrates the point, doesn't it? That, you know, for a practical configuration at low enough frequencies, you can get a scattering reduction. But, you know, whether you call that cloaking or not, Graham, Seb, I don't know.
Yeah, I mean, I think it is cloaking, you know, in the sense of the infinite Platonic solid, right? Then you have, then that corresponds to the fact that you can do everything with monopoles and dipoles on the surface.
Yeah, sure.
And so that's what I would think of the higher Platonic solid, reflecting the fact that you can just need you know, you can get by with lower order multipoles at those points. That's how I'd interpret that.
Yeah.
But okay, let us imagine we have a single source. We have a smooth sphere. The sphere is smooth. Okay, we have a sphere. How much can we reduce the scattering cross-section of the sphere just with a single source? By how much? You know, that's interesting to know.
You have to ask Daniel Onufray that.
Yeah, but you know, we would because, well, you know, if you can reduce the scattering cross-section, let's say even just by 50%, that's already great, you know. I mean, if you can do this, I mean, I'm sure that there would be tons of applications. I just, I mean, just, you know, stealth technology.
I think that one of the key things is I think you may have mentioned, someone may have mentioned it, the kind of instability, the fact that, you know, you move the source a little bit, you know, it's very, very dependent on the phase, isn't it? So you move the source a tiny bit, you know, or you get your measurement of the incident field wrong, you know, and it's very, very bad. I think that's the problem. I think that's probably what's held it back to a great extent, because obviously, you know, there's all the stuff from the 1980s, was it, with Nelson and Elliott, with, you know, active control and that sort of thing, and that's, I think that's been extremely successful. But it seemed to be the case from speaking to Steve Elliott that you know, it was almost kind of the machinery around it that sort of was the limitation rather than the actual theory. So it was the fact that, you know, you had to have transducers, you had to have sensors, you had to have kit, and that was the thing that restricted you. And I mean, maybe that's, well, it will have got a lot better, obviously, in 40 years. So you would imagine that things have moved on. There's been a bit of a resurgence, hasn't there? So maybe that is the case. I know Sir Elliott's still doing a lot of that stuff in ISVR now with Jordan Cheer. more in a kind of engineering perspective, but it's very good work. So if you want to know the answer to that question, actually, Seb, they may actually be good people to speak to, because they have a very practical hat on. They go in an anechoic chamber and set these experiments up, and so it may even be worth looking at some of their papers.
And also, there was one aspect, I mean, you insisted a lot upon that. You said, really, provided we create a cloaking region, the object itself doesn't matter much.
Yeah.
Okay, from the theoretical perspective, but from the experimental perspective, I would be keen to see this happening.
Yeah. I think especially if you have something with sharp corners, or that's going to have sort of diffractive effects. I think if it's a smooth object, it shouldn't be too bad. But of course, that is an attractive aspect to the theory. I found that absolutely fascinating ever since I read the original papers of Graham and co.
Oh, it's really
one very important point in your demonstration was you were looking at this quiet area in the middle, but from the cloaking aspect, you would rather consider something like hard boundaries, an object that is actually just rigid, and you would like to cloak that one. That would somehow bring much more of the perturbation, and the sources you would actually, I mean, you have to place them on the surface of that object. Physically, I mean, in a realistic way. Of course, you can say that they are floating in the fluid, that they are not connected by any means, but just from for a practical reason, if you can just design them, it would look like more like a meta surface at the end, because you have an object, you have an incident wave coming on it, and then if you can glue like a few patches or some stuff around, experimentally, it would be much easier. Because as William was saying, I mean, it's very important. The phase is important. You could use the same active parts actually to deliver the sound, for example, and to sense it also. But it's something that has to be almost adjusted in real time, which is actually possible. I mean, if we are talking about acoustics, we are not talking about extremely high velocities.
Yeah, exactly.
Electromagnetism, of course, it would be very, very hard to do stuff like this. Yeah. But in acoustics, it's something that maybe you put all this stuff in a nice proposal and send to the US Navy. Maybe there is a possibility. But don't take a side.
Muammer, accept that it's not the US Navy, it's the Royal Navy.
The Royal Navy. Okay, sorry.
Yeah. No, it's.
I think, I mean, again, I assume, I'm sure they're already looking at it. I mean, I know that again, ISVR do all sorts of stuff in that. I think that's the point. They look at the kind of very practical regimes, but again, I have a strong suspicion that it's the sort of machinery of it. There's technical aspects that are pretty critical there. Yeah, you're right, Muammer, absolutely. The configuration is obviously critical. You like you say, you've got these things floating in air, so you have to somehow connect them to. And at the moment, they're point sources. They're not finite. Although Chukkim has done some stuff on that. So if you have finite sources, then obviously they themselves scatter, and you can correct for that. It's pretty straightforward. It's just the multiple scattering problem, but it still needs to be done.
Yes, right.
Sorry, Muammer. Sorry, Muammer. What did you say?
No, I said that's perfectly right. I mean, that's a very. I mean, it's just the practical. I mean, it would not change anything from your theory, but you have to take into account, obviously, all the, let's say, the reflection from that object too, or not emission from along one side.
Yeah, exactly. Yeah.
But honestly, I mean, from some of this application, I mean, I don't know, for example, for the submarine at which wavelength they're operating, but this is something that, from the practical point of view, it's not so hard. I mean, you have all this noise cancellation that are actually part of the research in aeronautics. So people making this piezo patches too. So this is not something like just a mathematical dream that only guys in the mathematical department can can look at. But actually, it's something that is for the sound applications. That's something totally feasible to my understanding.
Yeah, I agree. I was hoping some of the metacluster stuff, you know, could lead to kind of Willis type materials. You know, we started talking about this a little bit, Seb. But you know, that's exactly what you want, is to have this kind of low frequency dynamic response. That's a strong response, because obviously that's the key thing in terms of realizing Willis materials, is the kind of, you know, it's always a weak effect, isn't it, in terms of the coupling tensor. So and you know, obviously various people, including some of the people here, have done nice work associated with, you know, realizing Willis type structures, especially in acoustics, for example. But in elasticity, it's quite hard, right? It's quite difficult. Even though it's kind of natural, even though it naturally falls out of the analysis, it's still quite difficult to sort of envisage how you would create a structure which sort of engenders that effect, you know, in terms of symmetry or asymmetry or whatever you need.
I mean, I agree on this elastic part, but maybe one could come up with, I mean, when you look at the pressure to elasticity, it works quite well with the piezo patches and stuff like this. So of course, it's there is some engineering part, but I mean, we are rather free to engineer these meta surfaces. You wish you can create anything as you. I mean, you can put, of course, something that looks like a dipolar, but you could even put something that looks like a toroidal. I mean, in the way of generating some inclusions.
Yeah, sure, absolutely, yeah. I think it's just the whole machinery is quite hard, isn't it? The homogenization in elastic dynamics, and that, you know, it's quite a lot. It's a long process to go from A to B.
Yes,
that's the point.
Yeah.
As you well know, Mother.
Yeah, no, I agree. I mean, in the general case, in acoustics, it's rather easy because you just care about the pressure field that is radiated or not radiated.
Yeah.
Which simplifies somehow the fact that it's mainly the surface normal to that is you just have to consider this kind of perturbation.
Yeah,
when it comes to the elasticity, well, you have all these in plane, out of plane motions that might be much more tricky. But in any case, I would say from the application point of view, it's, I mean, either for the submarine, the airplanes, and all these technologies, it's mainly solid to fluid. That is the interesting part. I think your formalism has a good chance to work there.
Yeah.
Guys, we should actually, you know, take this opportunity to talk with William of the possibility to, there is a special event next week, special webinar event, and there will be a round table. The round table will be at which time, guys? It will be at what, 4 p.m.? So next time, it will be Martin Wegner giving the talk first, then there will be a round table, and then there will be a mathematician giving another talk. And so, Bogdan, can you give us the timetable? So you would be interested in